So remember when we did those energy bar charts earlier in the class? We were specifically looking at physical changes, and then as a result, we ignored any change in chemical energy because, well, there was none. Now that we are concerned with chemical reactions, we want to show how the chemical energy changes as well. In our lab, we decomposed a small amount of sodium bicarbonate. In order for this to happen, we had to add heat to it. We can actually add that into our chemical equation to indicate that the reaction would not have occurred without the addition of energy. Since we added heat and it caused the reaction, we would add energy to the reactant side of the equation. To create our energy bar chart then, we first need to define our system. In this case, our system simply consists of sodium bicarbonate, so we will put that in the circle. For a chemical reaction, we are not going to consider phase energy changes because there is no change in phase. We heated the sodium bicarbonate and yes, a gas was formed. However, the gas itself was not sodium bicarbonate. It was carbon dioxide. So no phase change occurred. So let's look at the initial thermal energy. The sodium bicarbonate is at room temperature, so it does have some thermal energy associated with it. In the past, we have typically indicated room temperature as 2 bars. The particles themselves also have a certain amount of chemical energy associated with them simply because they are particles bonded together. We don't really know how much this is at this point, but we do know that we had to add heat energy in order for this reaction to occur. So we can assume that the particles initially have a fairly low amount of chemical energy. So we can just say that they have 2 bars of chemical energy. Then we added heat to the sodium bicarbonate. Think about that for a second, what actually needs to happen for a chemical reaction to occur. The particles need to collide and rearrange, but not all collisions cause a reaction. The orientation and velocity of the particles determine whether or not the reaction is able to occur. Faster moving particles are able to break the bonds that are already in place. So particles that were content there when they are at room temperature are able to break apart when heat is added. So there's an intermediate step here where the thermal energy of the particles is increased. Increasing the speed of the particles allows them to begin reacting. However, this change in temperature is only temporary. The sodium bicarbonate breaks apart to form water, sodium oxide, and carbon dioxide gas. The heat energy that we added will actually now be stored in the bonds of the new compounds that are formed. So when we add that heat energy, it causes the particles of the sodium bicarbonate to rearrange into new compounds. In this case, water, sodium oxide, and carbon dioxide. Since this rearrangement required energy for it to occur, the products must have more energy stored in their bonds than the reactants did. So when all is said and done and we take the heat away, the products will be at room temperature, but the chemical energy of the particles will have increased. This is what is called an endothermic reaction. Endo means into. So heat energy is added to the reactants. This energy initially increases the thermal energy of the reactants, causing the particle collisions to increase and the reaction to occur. The additional thermal energy gets stored in the bonds of the particles of the products, resulting in a higher chemical energy than the bonds of the reactants. In a typical textbook, you might see a graph similar to this one. Note that this is not a temperature curve, but it shows that the reactants start with a small amount of energy. Energy is added and stored in higher energy products. Note that this is not a temperature curve, but it shows that the reactants start with a small amount of energy. Energy is added and stored in the higher energy products. Not all reactions require added energy to occur, however. Some reactants start out with a high amount of energy in their bonds, but when put together give up an excess energy. In this case, the products have less energy stored in their bonds than the reactants. This is called an exothermic reaction. A good example was our zinc chloride lab. Many of you noticed that the beaker with the zinc reacting with a hydrochloric acid got significantly warmer. This was that excess chemical energy leaving the system and being given off to the environment.